Okay, so to understand the challenges of this so-called velocity pressure coupling, let's first look at our governing equations. And for the time being, for the rest of this class, well, I wouldn't say for the rest of this class, but at least for the time being, we'll assume that gravity is negligible. Okay. Now, gravity poses certain additional problems, which we will talk about down the road. The way you calculate pressure and everything changes when you introduce gravity. But we'll talk about that. We'll also assume that flow is 2D, okay, simply because our equations are shorter that way. Instead of writing 9 terms, we write 4 terms and so on, okay. And it's isothermal, so we'll not deal with the energy equation right now, but we'll talk about that later. And then we'll also assume that this is steady state. We are seeking the steady state solution, okay. That doesn't mean that we can't develop this algorithm or all this discussion cannot include transient, but for simplicity, we'll assume steady state. As you know, I've already told you this before, that in the pressure-based method, which is what our main focus is, when we seek steady state solution, we solve the steady state equations. We don't time march the equations to steady state, okay? So that's why we are starting from the governing equation in steady state form. So here's our steady state continuity equation. Notice that there is no time derivative in this equation, okay, because it's steady state. Also notice that density is within the derivatives, which means I'm not making any sort of assumption that density is constant or the flow is compressible versus incompressible or any of that, okay. In general, density is a variable. It changes with space, okay. Here's our momentum equation, and clearly you see the nonlinearities. For example, I have a u times v, and so on. Okay. On the right-hand side, notice that the only source is this pressure gradient, which drives the fluid. Okay. There is no body force. I've neglected the gravity. And then similarly, y momentum equation. And notice that I have written the advection and diffusion fluxes side by side, just like we did for the standard advection diffusion equation so far. Okay. So I've marked all the unknowns in these equations in color, red color. So our unknowns are, as we know in the pressure-based method, our unknowns are the primitive variables, u, v, and p. We are not solving for rho u, rho v, rho w like we do in density-based methods. Okay. Here we're solving for the primitive variables u, v, and p. Okay. Now all 3 unknowns appear in the momentum equations, as you can see. Here's your u, here's your v, here's your p. Okay, same thing here, p, v, u. But the continuity equation does not have a p, has only velocity, u and v. Okay. Now, why is that problematic? Well, the problem there is x momentum equation, let's say, represents force balance in the x direction. We know that. This is Newton's law of motion, the component in the x direction. Okay, this is basically force is equal to mass times acceleration. That's what it is. Or you can say rate of change of momentum is equal to the sum of external forces. Okay, that's what the Navier-Stokes equation is. So x momentum is momentum conservation in the x direction. And you would tend to think that, okay, that equation will give me the u velocity. Right? If you did force balance in the x direction, you would tend to think that would give you the rate of change of displacement in the x direction, which is u velocity. Okay. Similarly, the y momentum would give you v velocity. Okay. This is kind of pretty intuitive that I have x component gives me x component of velocity, y component gives y component of velocity. That leaves me now with the continuity equation, which should now, based on this list here, give me pressure. Because this guy gives me u, this guy gives me v, this should come from this third equation. Unfortunately, this third equation has no p in it. And that's where this whole business of pressure-velocity coupling comes in, and that's why it's so challenging. One of the quantities that is key to finite volume formulations is the mass flux across phases. So they identified that this is very, very important, how we compute the mass flux. Okay, across phases. Now, to compute mass fluxes across cell phases, we need velocities at the cell phases, right? Now, velocities are calculated at cell centers, not phases. We know that already. all quantities are calculated at cell centers, but we need phase velocities because ultimately the continuity equation simply says rho u at the eastern phase minus rho u at the western phase plus rho v at the northern phase minus rho v at the southern phase is equal to 0. Okay. So this requires some kind of interpolation, and people found that if you used distance-weighted interpolation for calculating cell phase velocities, the solution flip-flops between one or more solutions, okay? And this is referred to as checkerboard pressure oscillations. This is something you'll see in the literature quite often, that they'll say, okay, to remove checkerboard pressure oscillations, we used artificial fourth-order pressure damping, something like that. Okay, now we will talk about all those things, what those things mean and what people are actually doing. Okay, but I'm just telling you chronologically what happened. So in the 50s, people said, okay, we have this nice grid, which is the grid that you use for your advection diffusion equation. So they said, okay, we are going to discretize the momentum equation x and y on that grid, okay? And for pressure, we are going to solve this pressure Poisson equation that we have derived on paper with whatever boundary conditions we have derived, and they found that that doesn't work. Okay, so then they started looking at what may be going on, and they found, okay, at least by numerical experimentation, maybe not, really nailed down what the problem is, but they found that every time they used distance-weighted interpolation from cell center to phases, it did not work. Okay. So in 1956, to address these checkerboard pressure oscillations, Frank Harlow, who is, I recently met him at a conference, he's in his 90s now. He's a pioneer of sort of CFD, still at the Los Alamos National Lab Fluids Engineering Division. Okay. He is the first one who proposed that we solve the momentum equations and the continuity equations on different grids. Okay, and his method in those days was called the marker and cell method. This is 1956. I mean, we're talking about way before the advent of modern day computing. Okay. So he found that if I solve the momentum equations and the continuity equations on different grids, then I can actually get a converged solution. And he called this the Mac method, and the grid that he used, he called it the staggered grid. Okay. So that was the whole idea. Now, of course, Harlow's method was a completely explicit method. Okay. Later on, the simple algorithm that we're going to talk about is an implicit method, but this one is a completely explicit method. Okay. All right. So let's talk about what exactly is this staggered grid. So I'm giving you here a pictorial representation of a staggered grid versus a collocated grid. So in a staggered grid, here is what happens. So I've drawn a control volume here. Okay. The green control volumes from this point onwards in my notations represent pressure and all other scalars. So everything that is a scalar, for example, pressure, temperature, concentration, your material properties like gamma, they're all going to be stored in this, at the center of this green control volume. Okay? Then we stagger that. We take that control volume, shift it to the left. Okay? And we have this red control volume with a square, solid square in the middle, which is the cell center of that control volume. That is where the grid on which you're going to solve your X momentum equation. Okay, you take that same pressure grid, displace it to the bottom by half delta y, and now you get that blue control volume with a solid triangle in the middle, which represents its cell center. That's the grid on which we are going to solve our y momentum equation. Okay. So it's still a control volume approach or a finite volume approach, except the control volumes we use to conserve momentum and the control volumes we use to conserve mass are different. Okay. And you know, becomes kind of tricky because you can't just label one point and say, okay, that's my node I comma j. It's basically a combination of those three. So usually it's represented by this kind of elbow-like structure, and some people call it a dog's leg. Okay, so that whole thing is your I comma j, or your node naught. Okay. So that's what a staggered grid is all about. In the next slide, I will show you a picture of what it looks like when you discretize the whole domain using a staggered mesh. Okay. Now, a collocated mesh, you all know this. This is what we've been using so far. You just have one control volume with one cell center, I comma j or node naught, and all quantities are stored in there. Okay. So later on, after we have covered staggered mesh, we will move on to Navier-Stokes formulation for collocated mesh. And there, U, V, P, everything will be stored on that one point. Okay. Any questions so far? So here's what a staggered mesh looks like. I mean, it's pretty complicated. You can see there are the red control volumes, the green control volumes, the blue control volumes, and I've denoted here, for example, I don't want to mark this up any more than it's already. It's pretty cluttered, but here you can see this is your central node, and then your eastern node, western node, northern node, but each one of those so-called nodes is now essentially a dog's leg. Okay, and there are control volumes around it. All right. Now, one of the important things to also notice is that, for example, on the left wall, you have those red cell centers. Remember, red is for x momentum. Okay. So this is almost like a finite difference situation where we are saying that the u velocity at the boundaries are known at the left boundary, and the u velocities at the right boundary are also known. Okay. You know, if I were to do a standard finite volume formulation for a collocated mesh, then this guy would actually be here. This is where I'm going to have my first u. This would simply be a boundary. Okay, with no node there. But staggered mesh, it's different. The u velocities are known on the left and right faces. The v velocities are known on the bottom and top faces, or the south and north faces of the computational domain. The pressure is not known at any of the boundaries. There are only, as you can see, the green dots are only interior. Okay, some of these dog legs are sort of truncated. As you can see, this one is an incomplete dog's leg. Okay, only the U is there. There is nothing else beyond it. Okay, there is no pressure grid right here. Okay, same thing here. This is really the bottom of a dog's leg right here. Okay, so it's kind of weird, and you will see later one of the big problems with this kind of a mesh is interpolation. It's very non-intuitive. Okay, but we'll get to that in a moment. But this is the overall picture. So I want you to keep this picture in your head. In fact, the problem that you will be solving for homework 5 is on a square domain. Okay, it's the driven cavity problem, classic benchmark problem. But you will solve it with a staggered mesh, and this is really the mesh arrangement that you'll be using. So one thing you can do when you develop your equations is just print this out, okay, and then start from here. Instead of you having to draw it all over again, you can just use this as a template. Okay. Any questions so far? All right. So based on the indexing schemes shown, what is the span of these indices that we are looking at? If you look at here, P, you see here, this is 1 comma M, right? 1 comma 1. So this is my column number 1, right? So it goes all the way from 1 to N, and then here 1 to M. So that is like your standard finite volume, because if you look at the green control volumes, they are exactly like what a collocated mesh would be. Okay, just fills up the entire space. All right, so pressure, your solution for pressure will scan those indices 1 to N and 1 to M. Okay, now the solution for U or X momentum is kind of weird, because as I said here, this is your node number 1 for U momentum. That's already known. You're not solving for it. Similarly, this guy is already known. So you're really solving starting from 2 and then this is of course n. Okay, and in the y direction again, you're starting from 1. This is actually, this node here is 2, 1, right? Because there is no red control volume on the boundary here. So you're starting from 2, 1, and then here you're going up to 2, m. Okay? So in the x direction, or sorry, 2, m. So in the x direction, you're going from 2 to n. In the y direction, you're going from 1 to m. Okay? Which is kind of weird if you think about it. So that's your span for the x momentum equation. And similarly, if you go back and look at it in the y direction, obviously these get switched. Okay? You go from 1 to n and then 2 to m. Okay? So keep that in mind. That's very, very important. This is different from a collocated mesh. In collocated mesh, all the variables you would go from 1 to n, 1 to m. Because it's a finite volume approach. There are no nodes on the boundaries. But in a staggered mesh, it's different. Okay? Because of the way the control volumes are staggered. So now one question that one might ask is how the heck does this help? Why are we even doing this? I mean, if it's so complicated. Okay? So very important to understand this. So here's my staggered mesh, just a stencil. So first of all, you see, to solve my x momentum equation, let's say I solve my x momentum equation. So in that case, I'm looking at this control volume right there, marked in red. Okay? To solve for the x momentum equation, on the right-hand side of my equation, let me go back. I have this guy, right? So I'm going to integrate from west to east of minus dp dx. That's the basic finite volume approach. You integrate it over the volume. Of course, there's a north to south integral also, but one of those integrals is that. So what does this give me? This gives me basically p west minus p east times delta y after I've integrated it twice. Because this is an exact differential, right? So the first integral would simply give me p west minus p east, and then you do the second integral, it will give you the delta y. So it requires phase pressures of the control volume on which I'm conserving momentum. Got that, everybody? So if I'm conserving momentum on that red control volume, I need the pressure here and the pressure here on those two faces for the x momentum. Look at this grid. That's the beauty. The pressures are already being solved right there. You don't have to interpolate the pressures anymore. The green points are your pressure nodes. Okay, you already have the pressure there. If I'm thinking about solving the y momentum equation, this control volume, I need pressure again on that face, the northern face and the southern face. And they're right there, the green dots. So this grid is designed such that, okay, you need phase pressure, they're readily available to you, no interpolation necessary. Okay, now you think about continuity. Okay, let me wipe this out so it's clear. Continuity is being solved on this green control volume because that's my pressure node, right? We are solving for pressure using the continuity equation. So I'm conserving mass on that green control volume. To conserve mass, what do I need? I need u velocities on that face and v velocities on that face and that face. Again, readily available to me. That's where I'm solving for those velocity components. Okay? So by using this staggering, we have completely eliminated any interpolation. Not necessary at all. Neither for pressure nor for velocities. Okay? So earlier we were talking about this issue that the moment we use distance-weighted interpolation to calculate cell phase velocities from cell center velocities, we get these checkerboard pressure oscillations. Now, by staggering, what we have done is we've completely eliminated any interpolation. Okay? So this was what Harlow contributed to the field of CFD. He's the first one who came up with this idea that, okay, this is how we can eliminate an interpolation. Okay. So all three requirements are readily met without having to perform any cell-to-face interpolation. All right. So, and because of that, what people have found over the years, and you will also find it, hopefully, when you do your homework, is that a staggered mesh completely eliminates checkerboard pressure oscillations. Okay. All right. So, based on our previous discussions, see lecture 8, slide 8. So, this is our advection diffusion equation with first order upwind and central differencing for diffusion. Now, what I have not done here is I have not used any interpolation for these link coefficients. I have retained the face values as is. Okay. Notice that I'm not writing this as mu east plus mu naught divided by 2 and so on. I've kept it as mu east. Okay. Same thing here. I've retained these velocities at the faces. I'm not writing them as anything else. Okay. So that's one thing to understand. The other thing I want to point out is that, again, I've talked about this many times. The way, so you have a rho u, for example. The way you treat this part and the way you treat that part are different. Okay. This is where you need the interpolation that I was talking about to calculate phase velocities from cell center velocities so that you can calculate your link coefficients. This is where you are using the scheme that we've talked about for advection so far. Okay, the two are completely different. One, we think this first part here, we think of it as simple interpolation. The second part is where we start thinking about how do we treat the phase value of phi. In this case, phi happens to be one of the velocity components. It's the advected component, okay, rather than the advecting component. This part here is the one that advects. This part here is the one that gets advected. They're two treated completely differently. Okay, the one that gets advected has to follow this physics that we talked about, that it gets advected in the direction of the wind. Okay. But this part here is different, treated differently. So keep that in mind that, yes, this is a nonlinear equation, and one, you know, if you start thinking about it, you might argue, well, why? I mean, the two U's are the same. Why should we treat them differently? But that's the way it is done. We tend to think of them as one being the advecting component because it's really the mass flux that's carrying the information, and the other is the information that it carries. In this case, it's the velocity component that it's carrying. Okay. So all this issue that I'm talking about of cell-to-face velocity interpolation is really relevant to this first part. For the second part, we are still using first order upwind like I've said here. Okay? Everybody clear on that? Because there is no interpolation there at all. This is just an upwind differencing scheme. And then on the right-hand side, you now have your pressure source. And like I was saying, you have to, this is basically the integration over the volume for a Cartesian mesh. Okay? So the source is somewhat special in this case. This is not a volumetric source. As you can see, there is a gradient. So we want to, you know, evaluate it more accurately rather than saying this is just dpdx at naught times delta x times delta y, because it's an exact differential, so we can do a better job of integrating it. Okay? Rather than making an approximation. And this is something I've already talked about. UD applied only to the second U, not the first. The second U is treated as an advected scalar. All right, next we simplify all terms using a staggered mesh arrangement. For the X momentum, our central focus is the red control volume. Okay, so I'll just mark it here. This is what we are looking at. That's where we are conserving our momentum. Okay. So let's start with the source term. Source term is that we integrate it once, we get P east minus P west, right? Because this is an exact differential. So you're simply going to get P east minus P west. And then we have the dy, and of course this we approximate. Okay. So this really becomes the average pressure on the eastern face and the average pressure on the western face, okay? Which is denoted by these guys. And notice that according to our index here, this P east, P at the eastern face of the red control volume is nothing but P naught itself, because this whole dog's leg is not. Okay, so this guy is nothing but equal to P naught. All right, because this is my node naught right there. And this guy here, okay, you can see if I put a red, this is that dog's leg. That is my western node. I've marked this one by west. I didn't write it here, but that's my western dog's leg. Okay, so really this is P naught, and then this guy is P capital west. And of course, you know, I factored in the negative sign, so you get P west minus P naught times delta y. Again, like I was saying before, no interpolation necessary. So again, we are trying to conserve everything on the momentum control volume, which is the red control volume. We have figured out what to do with the source. Now we have to figure out what to do with the left-hand side of the equation. The left-hand side of the equation has quantities such as U east, U west, V naught, V south, and so on. Okay. Now, if I look at the red control volume, I do not have U east, U west, V north, V south, and so on the faces. Okay. So here we are saying we are still going to use standard central difference. All right. Now, it is standard central difference, but one of the things you have to be careful with is because of the staggering, the interpolation is very non-intuitive. So, for example, U east, if you look at this expression here, this is pretty intuitive. U naught plus U capital E is divided by 2. Same thing here. But you look at V naught, this is totally different. Okay? And this is where the staggering messes up everything. So what are we saying? We need the V velocity right there. That V velocity, we are saying we are going to take an average of this velocity and that velocity. Those are where my nodes are. Okay? So it's north plus northwest divided by 2. That's average of this and this. Okay. Similarly, for the southern face, I'm doing average of this and that. That's what you have here. So these two are pretty non-intuitive expressions. You actually need to draw a picture to convince yourself that this is what I should code in. Okay, you simply can't say, okay, V naught is V naught plus V naught divided by 2. That's not going to work, because then that will give you the velocity here. Completely different geometric location. Okay? Everybody clear on that? What we are doing? If anybody has questions on this, please stop me. All right? This is important to understand. Okay, so when it comes to density, it's even more complicated. Okay, now go back to your equation here. So I'm writing it as this way, rho u east, but what this really means is rho east times u east, right? That's what it means. We are not treating them together because the interpolation is completely different for the two variables. So we are saying, okay, we figured out how to do u east, for example, here. We also need to figure out how to calculate rho east. We need to find density at this face, that face, that face, and that face. Okay, because we need rho east, rho west, rho north, rho south in those expressions. So how do we do that? Now here is my rho east. Eastern face of the red control volume. There's a node right there for scalars. So density is directly available there. That's rho naught. Okay? So this is my node naught for density. So that's this. Then I go to the western face. The western face is nothing but rho west because, as I said, this is my dog's leg right here. Okay? So that's my western face. Northern face here, big problem. I mean, as you can see, there's a green node here. There's a green node here. There is going to be another green node up here. and another one up here. I want to find the value of rho right there. So it's going to be a 4-point average of this node, that node, that node, and that node. So it's a 4-point average of rho naught, rho west, rho north. Okay, this is my northern node, and this is northwest. Okay, now of course, this is all part of one dog's leg, so that's why I labeled this also as northwest. Okay, so it's a 4-point average of rho naught, rho west, rho north, and rho northwest. Same thing for the southern. If I want to calculate this one here, it will be a 4-point average of these 4 values. So you can see rho naught, rho west, rho south, rho southeast, southwest. Okay. So 2 of those densities you get directly. 2 of those you have to use a 4-point interpolation. Okay. And the way you can see from these expressions right away, they're right in front of your eyes, the way you interpolate density is very different from the way you interpolate velocity, because velocity and density are being stored on different grids. Okay, it's not the same interpolation. Any questions on that? Okay, same for mu. So whatever I've used for rho, the same applies to mu, because mu and rho are both scalars. They will be interpolated the same way. Okay. So all these guys here, you need to figure out, it will be the exact same expressions that you used for density. All right. Okay. So after you've done all that, your link coefficients for the momentum equation would look like this. Now, of course, I haven't written out the full expressions for each of those phase densities, phase velocities, and so on. But that's not how you would do it anyway. When you're writing a code, these are your link coefficients. But what you will say is my u east is this expression. My rho east is this expression. My mu east is this expression, and so on. So you will have, in this case, I guess you will have 3 times 4, 12 different expressions. Rho east, u east, mu east. Rho west, u west, mu west. Rho naught, v naught, mu naught, and so on. 12 expressions. And then you will code in these link coefficients. Okay, exactly as they are on paper right now. So do not try to take those other expressions, substitute these in here, and then come up with a bigger expression and code that in. It's not going to help your coding. You'll make mistakes. Okay? But be that as it may, these are the link coefficients that we have for the x momentum equation. And the source term we have already derived. This is what the source term looks like. The only difference between these link coefficients I have here and the ones I had for the general advection diffusion equation is in the way you calculate each of those terms, not in the link coefficients themselves. Because the link coefficients themselves come from standard finite volume formulation on a grid. Okay, nothing is different. It's just a different grid control volume you're using. All right. So it's those 12 expressions that I talked about at the front end that will become different now, but not these expressions. Okay. And then finally you assemble it all together. I'm using the superscript x for the x momentum equation, and the reason for that is you will find out very soon that the link coefficients for the x momentum and the y momentum will be different, because one of them is the conservation equation on the red grid, the other is the conservation equation on the blue grid, and the way the interpolation is done for the exact same quantity will be different. For example, the way you calculate rho east for the x momentum equation will be different from the way you calculate rho east for the y momentum equation, because it's a different eastern face you're looking at, not at the same location anymore. Okay, so keep that in mind, that those 12 expressions I talked about will be different when you go to the y momentum equation. Okay, so that's why our link coefficients, the final values we calculate for these guys, will be all different for the y momentum. Okay, even though these expressions may look similar. Okay, so let's talk about the y momentum equation. Exact same thing. You change your second u to v. And this is where, we keep talking about this, that one is an advected scalar, the one is the advecting scalar. So all I've done is I've changed these guys from u to v. That's all. There's no other change. Okay? So everywhere you had, and of course these, the diffusion, everything has changed there. U's became v's, and then the dp dx got changed to dp dy. All right? But this front part here, these guys, no change, same. Okay? So second v is treated as an advected scalar, and upwind differencing is applied to it. We talked about that. Now we simplify everything again, but now on the blue control volume. Okay? So we are first going to figure out what our source term is. We take dp dy, integrate it. Notice that now I'm doing the south to north integration first, because that's an exact differential right there. Okay? And so we get P north minus P south, and notice that on this grid here, the northern phase pressure is nothing but your P naught, and the southern phase pressure is nothing but your P south. Okay, no interpolation necessary there. So that's what we have done there. Next we consider all the velocities. This is where you see things start changing. If you look at this expression versus what I had 2 slides ago, this one, they're different. Okay, it's not the same expression. So whatever code you wrote for the x momentum, you can't use that for the y momentum. You have to write it separately now. So this is where, because of the fact that the grid has staggered, these expressions are different. So I'll talk about V north and V south first. So you see here what I need is velocity, V velocity there. V velocity there is easily available by averaging these two guys. Okay. Similarly, V velocity at the southern face, easily available by averaging this and the next triangle here. Okay. Then I need U velocity at the eastern face, right there. How am I going to get that? Well, I have to use something different now. I have to use the average of southeast and east, these two guys. Okay, the two red points, I'm going to average those two to get the U velocity there. And similarly on this face, I'm going to average this guy and that guy to get the U velocity on the western face. So that's what these two expressions are. If you recall, in the other case, we had V north plus V northwest. Okay. Here we have U east and U southeast. Okay. Any questions on that? All right. So that's that. Now the rho interpolation, the scalar interpolation also changes, because now we are looking at what is my value of rho at this point. Earlier we were asking the question, what is our value of rho here? Because that was our control volume. Now we are asking the question, what is our value of rho right there? What is our value of rho here? What is our value of rho here and here? And so on. So you see the north and south are easy because there are the green points right there. Let me just wipe this out so you can see. So north and south are very easy. Green points directly on the face. Okay, so that's these guys here. And then the other two, to find the value of rho here, I have to take a 4-point average of this guy, a node here, and a node here. Okay, that's these two expressions, east and west. Okay, any questions? So very similar to X momentum, but you have to be careful. The expressions are different. Same idea for mu. As I said, density and mu viscosity follow the same procedure. So here is a final summary of the link coefficients for the Y momentum equation. Again, really nothing changed in these expressions except that, you know, the source term, for example, has south and north instead of west and north, and you know, some of the delta x's may have become delta y's and so on. But pretty much these expressions are the same, but the values, the phase values that you used from the previous slide are very different from the X momentum equation. Okay. Ultimately, you finally stored this in 5-band form. Again, I've used the superscript y to denote that these are link coefficients for the Y momentum equation. Okay. And this is the short form we've been using so far and will continue to use. Now, I'm not using n here, I'm using nb for neighbor. Okay. I think in some of the previous lectures I used n, but here I'm not using n because small n denotes the northern face. It gets confusing. Okay. So that's why I'm using nb.